Hi, welcome to another lesson of our study of linear algebra, and yeah, we're still going, and I thank you for just being part of this journey, and that you've not given up, and you really want to understand more about linear algebra. Thumbs up to you. Okay, so we going to talk about bases and dimensions, and what we can say about a set being a basis and a set being a span of a given vector space. Okay, a spanning set for a given vector space. So the basis for a vector space V is a subset. So that basis is actually a subset of the vector space such that the first thing is 1. The set you are calling a basis is linearly independent. So S here is linearly independent, and then S spans V, that is the span of this set, gives you the entire vector space. The dimension, on the other hand, written as dim of V, is the number of vectors in your basis. Okay, so if I have 4 vectors in my basis set, then that is my dimension of the vector space. So an example is having the set S giving us 1 0 as one vector and then 0 1 as the other vector. Okay, I normally use this because this is a standard basis I can come up with. All right, so then I'm saying that this S is a basis for the vector space R2. How do I know that this is indeed a vector space of R2? I'll know that one by showing that, so the first part is showing that this is linearly independent. If you've been following our lessons, realize that this is indeed linearly independent. I'm just going to show it again, but with a very fast space here. A1 into 0 1 plus A2 into 0 0 1 should give you the 0 vector, which is 0 0 in terms of R2 here. And if you do the distribution and simplification, you're going to have A1 comma A2 being equal to 0 0. Yes, if you have two vectors, we are saying they are the same, then A1 should be equal to 0, A2 should be equal to 0. And then if I'm able to show that this happens only when both A1 and A2 are 0, then since we've been able to show that A1 is equal to A2 and is equal to 0, then indeed the set S is linearly independent. Okay, so S is linearly independent. Now the second part that we are supposed to show is to show that the span of S gives the entire R2. So what is span of S? The span of S here will be defined as a scalar multiple, say A into or A1 into 1 comma 0 plus A2 into 0 comma 1, and that is, I mean, if you've watched a video on linear combination, then the span of a given set is just simply the linear combinations you can get from the given set. Okay, so that A1 and A2 are real numbers. Now if I sum these two, what I'm going to get is you're going to be A1 comma A2 like we had for here. Remember here, what we're doing was we're trying to equate it to 0. And so if you equate it to 0, we are going to have A1 to be 0, A2 to be 0. But here we are not equating this part to anything. We are just summing them, okay? So know that the difference. Say that A1, A2 are equal to, belong to the real numbers. Now what I'm going to do is I'm going to pick a general vector in R2 and show that that vector can be simplified as a linear combination, or can be written as this form: linear combination of the set of, or the elements in this set S. Okay, so if I pick a general vector x comma y in R2, so if you know R2 very well, that two-dimensional R2, realize that every vector you pick can be written as x comma y. So if I pick x comma y, I'm just representing it with all the possible points, or every point that you can think of. Okay, notice that x comma y, what I'm saying is I want to equate this to be equal to the span, or the general form of the span, which is A1 comma A2. So in this case, it means that a1 will be equal to x, and then a2 will be equal to y. So any vector I pick, s comma y, can be written as, so s comma y can be equal to x into 1 comma 0, that is my a1, plus y into s 0 comma 1, which is basically the x and y are just real numbers. So this basically belongs to the span of what? S. Because the s comma y that we've picked here is being expressed as a linear combination of vectors in the set S. Okay, so it means that whatever vector you can think of in R2 can be expressed as a linear combination of vectors in S. That means all the vectors in R2 belong to the span of S. So indeed, span of S here is equal to R2. Okay, and that is exactly what we wanted to show. So yes, S is the basis for R2. Now the other example is I have my S here, and the S here is a sort of these vectors, and these are matrices. Okay, so first we want to show that this is a basis for the vector space V equals M2 by 2. Now to show that, the first thing is to show that S is linearly independent, right? So you just pick some A1 into 1 0 0 0 plus some constant A2 into 0 1 0 0 plus A3 into 0 0 1 0 plus A4 into 0 0 0 1. This should give me the zero matrix. Okay, in the matrix 2 by 2 matrix, there's zero vector here is just the zero matrix. And so if I do summation, multiplication, everything, and I sum the matrix, I'm going to have A1, A2, A3, A4 here equals zero matrix. If you look at two equal matrices, then you can say that the components should be the same. A1 equals 0, A2 equals 0, A3 equals 0, and then A4 is equal to 0. So we've been able to show that A1 equals A2 and is equal to A3 equals A4. For this linear combination to be 0, all of them should be 0. So it means the set S is linearly independent. Okay, so the first part is shown. The second part is to look at the span of this S. The span of this S is equal to the linear combination A1 into 1 0 0 plus A2 into 0 1 0 and plus A3 into 0 0 0 1 plus A4 into 0 0 0 1. And like I said, notice that this is different from the part A, because the part A is equating your linear combination to the zero vector. Here we are not equating the linear combination to anything. It can be any matrix at all. So that A1, A2, A3, A4 are real numbers. Okay, so what's going to happen here is that we want to show that every matrix in a 2 by 2 vector space of matrices can be simplified or can be written as a linear combination of these elements or these ones. Okay, now what I'm going to do is that if I sum them, if you remember, if you sum them, this is what we had. Okay, so if I sum them, I'm going to have A1, A2, A3, A4, such that A1, A2, A3, A4 are real numbers. Okay, and if you look at it very carefully, indeed this is the general form of any matrix in the 2 by 2 matrix vector space. Okay, because if I pick any general matrix A, it can be written as A11, A12, A21, and A22. Okay, that is the general form of these ones. And if you look at it very carefully, these A11, A12, A21, A22 are numbers. Okay, so if I say that this, if I equate it to this span, which is A1, A2, A3, A4. Then this A11 here, this will imply that we have A1 to be equal to A11, A2 to be equal to A12, A3 to be equal to A21, A4 to be equal to A22. So what this whole thing is telling us is that this A that I've picked as a matrix, A11, A12, A21, A22, can be written as A1 is what? A11. So into the first vector I have plus A2, A12, sorry. A12 into the second matrix, which is 0, 1, 0, 0, plus A21 into 0, 0, 1, 0, plus A22 into 0, 0, 0, 1. Okay. So in this case, for any general matrix A, it can be written as a linear combination of the vectors in our set that we are looking at, and that is that belongs to the span of the S, because these are just values. Okay, they are real numbers, and that is the span definition. You've been able to show that in the scalars you want to choose, A1 is A11, and so if I pick a matrix, let's say the matrix 1, 0, 0, 1, then this is equal to so here A11 is 1, A12 is 0, so you can compare that. So this is equal to A11, which is 1, into 1, 0, 0, 1. I'm sorry, 0, 0. Here is 0, actually, sorry. Plus A12, which is 0, into 0, 1, 0, 0. Plus 0 into 0, 0, 1, 0. Plus 1 into 0, 0, 0, 1. And so this is an example of matrix that you can pick, and when you pick these, this will be your A1, which is the same as the A11 I have here, which is A2, which is A3, this is A4. So any matrix you can pick can actually be written as a linear combination of matrices or vectors in the given set. Okay, so this shows that this set given S is actually a basis for the M2 by 2 matrices. I want you to try this. Actually, I'll upload a video on that, which is a bit very difficult, or not that difficult. I would say it's a bit difficult compared to the rest. Is you want to show that this given other set 1, 1, sorry, 0, 0, and then 1, -1, 0, 0, 0, 0, 1, -2, and then 0, 0, 1, 2. There's also a basis for the vector space V equals M2 by 2 matrices. Okay, show that any matrix, any general matrix you pick, A equals A11, A12, A21, A22, can be written as a linear combination of these guys by showing explicitly the A1, A2, A3, and A4 in terms of these values. Okay. All right. Thank you for staying tuned, and then I'll actually, like I said, I'll actually do a video on this one. So stay tuned, and don't forget to subscribe to my channel if you have not subscribed. Like, share the video for other people to also, benefit from the same thing. See you in our next lesson.